Good morning, everyone, and welcome. Today, I'm excited to present an overview of SEC electrical compliance, covering everything from design through to commissioning. The title of our presentation is SEC Electrical Compliance Overview, and our focus will be on understanding how compliance impacts the entire process, including design, power, and approval. Over the next few slides, we'll explore the key steps involved, ensuring we're aligned on best practices and requirements. Let's get started. Let's take a closer look at the three-stage life cycle that underpins our process: design, construction, and verification. These stages form the backbone of how we develop and ensure quality in our projects. First, during the design phase, we focus on planning and creating detailed specifications. This is where we define what the system needs to do and how it should function. Next comes construction, where we actually build the system based on the design. This stage requires careful implementation to ensure that what we build aligns with our plans. Finally, verification is crucial. This is where we test and validate the system to confirm it meets all the requirements. It's about catching any issues early and guaranteeing quality before deployment. By understanding this life cycle, design, build, and verification, we can better manage complexity and maintain high standards throughout the project. This structure supports our overall goal of delivering reliable and effective systems. Let's take a closer look at the SEC system parameters for LV and MV networks. When we talk about LV or low voltage networks, we're dealing with the distribution systems that supply power directly to homes and small businesses. The parameters here are quite specific, especially regarding earthing, which is crucial for safety and system stability. Proper earthing helps prevent electric shocks and protects equipment from faults. Moving on to MV, or medium voltage networks, these are used for distributing electricity over larger areas, often between substations and the lower voltage distribution points. The parameters for MV systems are designed to ensure reliable operation and efficient power flow. Frequency is another key aspect across both LV and MV systems. Maintaining the correct frequency is vital because it affects the stability and synchronization of the entire power grid. Any deviation can cause equipment issues or even blackouts. Overall, understanding these parameters, especially earthing and frequency, is essential for designing and operating safe, reliable, and efficient power distribution networks. These details form the foundation of system stability and safety, which ties directly into the overall theme of system security and performance. When selecting a transformer for SEC projects, it's important to follow a standard approach to ensure reliability and efficiency. One common choice is the DINE 11 transformer, which is quite popular in these applications. The DINE 11 designation indicates that the transformer has a specific winding configuration and phase shift, which helps with system compatibility and reduces issues like harmonics. Next, we consider the ONAN cooling method, which stands for Oil Natural Air Natural. This is a passive cooling system that relies on natural circulation of oil and air to dissipate heat. It's a common and cost-effective choice for many applications, especially when the loading is moderate. Speaking of loading, it's crucial to properly evaluate the expected load to select the right kVA rating. Choosing a transformer with an appropriate kVA rating ensures it can handle peak loads without overheating or reducing lifespan. All these factors, transformer type, cooling method, and kVA, are interconnected. They form the foundation for a reliable, efficient, and safe electrical system in SEC projects. By following these standard selection criteria, we can ensure the transformers meet the project's demands while maintaining operational stability. Let's take a closer look at voltage drop calculation and its limits. When we talk about voltage drop, we're referring to the reduction in voltage as electrical power travels through a feeder. This is a crucial factor because excessive voltage drops can affect the performance of our equipment and overall system reliability. Understanding the feeder is essential here. It's the path through which electricity flows from the source to the load. As current moves along this path, some energy is lost due to resistance, which we call losses. These losses are inevitable but need to be managed within acceptable limits to ensure system efficiency. Calculating the voltage drop accurately involves considering various parameters such as current, resistance, and the length of the feeder. This is where precise calculation methods come into play, allowing us to predict and control voltage levels effectively. The SEC, or Standard Electrical Code, provides the guidelines and limits for voltage drops. These limits are set to ensure safe and reliable operation of electrical systems. Staying within these limits is paramount to maintaining system stability and protecting equipment. Overall, by properly calculating and adhering to voltage drop limits, we can optimize our power distribution, improve efficiency, and ensure safety across the entire electrical network. Let's take a closer look at panel fault levels and short-circuit protection. When we talk about fault levels, we're essentially referring to the maximum current that can flow during a fault, such as a short circuit. This is often measured as ISC, or the short-circuit current. Understanding ISC is crucial because it tells us the worst-case scenario for current flow, helping us design protection systems that can handle these extreme conditions. Protection devices, like circuit breakers and fuses, are selected based on these fault levels to ensure they trip safely and quickly when a fault occurs. This is vital not just for the equipment's safety, but also for the safety of personnel working on or near the panels. By properly assessing fault levels and implementing appropriate short-circuit protection, we create a safer environment and enhance the reliability of the entire electrical system. This ties back to our overall goal of ensuring both safety and efficiency in our installations. Now, let's take a look at the dual feeder system for critical loads. This setup is designed to ensure maximum reliability by utilizing two separate power sources. The key component here is the automatic transfer switch, or ATS, which automatically switches between feeders if one fails or needs maintenance. This redundancy is crucial for maintaining continuous power, especially for critical systems that cannot afford any downtime. By implementing a dual feeder system, we're effectively reducing the risk of power interruptions and enhancing overall system reliability. This concept ties back to our overall theme of ensuring resilience and dependable operation for essential infrastructure. Let's take a closer look at the SEC-approved low-voltage and medium-voltage cable types. These cables are specially designed to meet strict safety and performance standards. One key aspect is the use of XLPE, or cross-linked polyethylene, which significantly enhances the cable's thermal resistance and overall durability. This material helps the cables handle higher temperatures and provides better insulation. Another important point is the use of copper conductors, which are preferred for their excellent electrical conductivity and reliability. When combined with insulation materials like LSF or low smoke and flame retardant compounds, these cables become safer in case of fire, reducing smoke and toxic fumes. For medium voltage applications, these cable types are optimized to ensure efficient power transmission while maintaining safety and longevity. Overall, understanding these approved cable types helps us choose the right solutions for safe, reliable, and efficient electrical systems. Let's talk about cable trench depth and burial methods. When we're trenching for cables, it's crucial to consider the appropriate depth to ensure safety and durability. A common practice is to bury cables under a sufficient depth of soil, often covered with layers like sand to provide extra protection and prevent damage from sharp objects or shifting soil. It's important to remember that the depth varies depending on the type of cable and local regulations, but generally, deeper trenches reduce the risk of accidental damage. Additionally, installing warning tape above the cables before backfilling serves as a visual alert for future excavations, helping to prevent accidental cuts or punctures. Overall, paying attention to the correct trench depth and using proper burial methods like sand bedding and warning tapes are key steps in maintaining safe and effective cable installations. These practices align with our overarching goal of ensuring reliable and safe electrical infrastructure. Let's talk about cable bending radius and separation rules. When installing cables, one of the most important factors is ensuring the bending radius is appropriate. This means avoiding sharp bends that could damage the cable or impair its performance. Typically, the bending radius should be at least several times the cable's diameter, depending on the specific type of cable. Separation is equally crucial. Cables should be kept apart from each other to prevent interference and to maintain safety standards. Proper separation also helps in heat dissipation and reduces the risk of damage during installation or maintenance. Both bending radius and separation are key to ensuring the longevity and reliability of your cable system. By adhering to these rules, you not only protect the integrity of the cables, but also enhance overall safety during installation and operation. Remember, following these guidelines is essential for maintaining system performance and avoiding costly issues down the line. This is a fundamental part of the overall cable management strategy we've been discussing today. Let's take a closer look at the standards for CT and energy metering installation. First, CT, or current transformers, play a crucial role in measuring current accurately and safely. Ensuring they are installed according to standards helps us achieve reliable measurements. Metering accuracy is vital because it directly impacts billing and system monitoring, so following proper standards ensures our measurements are precise. Protection is another key aspect. Correct installation helps safeguard the equipment and personnel from faults or overloads. Lastly, polarity is often overlooked, but it's essential to connect everything correctly to maintain the integrity of the measurements and system operation. All these points tie back to our overall goal of creating a safe, reliable, and efficient energy system. Now, let's talk about insulation resistance and VLF testing. These are critical steps in ensuring the integrity of electrical insulation systems. First, we have test, which stands for insulation resistance testing. This measurement helps us determine how well the insulation is performing and whether it's capable of preventing unwanted current flow. A high insulation resistance value generally indicates good insulation quality. Next, we have VLF, or very low frequency testing. VLF is particularly useful for testing large or complex insulation systems, especially in high-voltage cables. It applies a low-frequency voltage to the system, allowing us to detect potential faults or weaknesses that might not show up with traditional testing methods. Both test and VLF are essential in the acceptance testing phase. They help us verify that new installations meet the required standards before they go into service. By thoroughly testing the insulation, we can identify issues early, reduce the risk of failures, and ensure long-term reliability of the system. Overall, these testing methods are valuable tools in our maintenance and quality assurance toolkit, giving us confidence that the insulation will perform as expected under operational conditions. Now, let's move on to slide 13, which focuses on MV switchgear commissioning and protection. When we talk about switchgear, we're referring to the crucial equipment that controls, protects, and isolates electrical circuits at medium voltage levels. Proper commissioning is essential to ensure that this equipment operates reliably and safely throughout its lifespan. It involves a series of tests and checks to verify that the switchgear functions as intended, including insulation tests, operational tests, and protection relay calibrations. Protection is a key aspect here because it helps prevent damage to equipment and ensures safety for personnel. We typically follow international standards, such as those outlined by IEC, to guarantee consistency and reliability across different systems and regions. IEC standards provide comprehensive guidelines on the design, testing, and protection schemes for medium-voltage switchgear. By properly commissioning and applying appropriate protection settings, we can detect faults quickly and isolate problem areas, minimizing downtime and preventing more serious failures. This process is a vital part of the overall project, connecting directly to our goal of creating a safe, efficient, and resilient electrical infrastructure at medium voltage levels. Let's take a moment to go through the complete SEC compliance checklist. This is a crucial step to ensure that every aspect of our project aligns with regulatory standards. First, we start with the checklist itself, making sure all necessary items are accounted for and verified. Next, compliance is at the heart of this process. It's about adhering to all security regulations and industry standards to protect data and systems. Moving on to design. This involves reviewing the system architecture to confirm it meets SEC requirements from the ground up. Then, installation, ensuring that the hardware and software are properly installed according to approved protocols. Finally, testing, rigorously evaluating the entire setup to identify and fix any issues before going live. Covering all these points thoroughly helps us maintain integrity, security, and compliance throughout the project lifecycle. Remember, this checklist isn't just a formality. It's our safeguard to ensure we meet all regulatory standards and deliver a secure, compliant solution. Let's wrap up by discussing grid reliability and the final system validation. Ensuring the grid is reliable is crucial for maintaining a stable power supply, especially as we integrate more renewable sources. Resilience is also key. It's about how well the system can adapt and recover from disruptions, whether they're natural or man-made. When we talk about power, we're focusing on delivering consistent, high-quality energy to all users. The SEC plays a vital role here, setting standards and overseeing the validation process to make sure the entire system functions as intended. Ultimately, these elements come together to ensure that our power grid is not only reliable, but also resilient and ready for the future. This final validation confirms that all the pieces work seamlessly, supporting our overall goal of a sustainable and dependable energy system.